Greetings of the day, dear students. In this video we are going to discuss about the slip torque characteristics of the three-phase induction motor. In this video we are going to see what are the important equations we are having, and what are the different variables or terminology we will come across, and also the graph in between the torque and slip for different values of slip, that is when the slip becomes equals to 0 and when the slip S equals to Sm and when the slip S becomes equals to 1. So for different values of slip, what would be the value of torque, what could be the value of torque, all those things we are going to discuss in this video. Right now, from our previous discussions we have seen that the full load torque expression is given by torque T equals to some K S E2 square R2 divided by R2 square plus Sx2 whole square. In this equation, S indicates the slip, and from our previous discussions we have seen that the percentage slip S is given by Ns minus N divided by Ns into 100, where in this context, for example, if you are having a stator and we are also having the rotor, where the stator is given the three-phase supply, and because of the resultant flux, right, it is rotating with some synchronous speed in the air gap with speed ns, but whereas this rotor is going to rotate with some speed n. Now there will be the relative speed between these two, rotor and the revolving or rotating magnetic flux, right? So this is what from our previous discussions. Right now, X2 indicates the rotor reactance at standstill and R2 indicates the rotor resistance. Clear? So here the ns dash, which is nothing but the synchronous speed in RPS, is given by ns by 60. Now in order to obtain the torque slip characteristics of the induction motor, we have to consider some of the points. For example, as and when the rotor is also rotating it with the synchronous speed, then what happens? This value of slip becomes 0, because when this n becomes equal to ns, the value of slip s becomes 0. Once the slip becomes 0, so we can observe in this equation, if s becomes equals to 0, then the torque also will become equal to 0. Very important. This point is very important. If in the three-phase induction motor, if rotor also rotates at synchronous speed, then obviously there won't be any difference in the speed. Then the slip s becomes 0 and the torque also becomes 0. But when the rotor speed is very much nearer to the synchronous speed, that means it is not equal to synchronous speed, but it is little bit lower than the synchronous speed, then what happens? This ns minus n, the value of slip will be low. The value of slip will be low, but not equal to 0, but it is low. Right now, at that term, once the value of s is low, Sx2 whole square value will be very low. Already the value of s is low, its square value will be very low. So obviously Sx2 whole square will be very low. Compared to what? Compared to R2 square. This Sx2 whole square value will be very less. Then we can neglect that. Therefore, torque T equals to K SC2 square R2 by R2 square. R2 get cancelled out, right? So in this equation, almost all the terms are constant except S. So we can observe here, torque is directly proportional to S when if S is low. If the value of slip is low, during that state the torque will be directly proportional to the slip. Under low slip region, the value of torque is proportional to the slip. This is very important, right? So here, this is the graph we can get here. At slip s equals to 0, if the rotor rotates at synchronous speed, torque is made 0, Now we can observe under low slip region the graph is linear. So this is the stable region of operation. This is the stable region of operation, and the operating point of the motor should be in this region. The operating point of the motor should be in this region. Similarly, at some particular value of the slip, the motor attains the maximum torque. Right? So if the value of slip S is equal to R2 by X2, that is the point where we is to get the maximum torque, and that torque is to be called as pull-out torque. That torque is pull-out torque. Clear? That torque is called pull-out torque. Now, so at S equals to Sm, the value of slip, at that point value of slip, the torque is maximum, that is called pull-out torque. Now with the further increase in the slip, if you are trying to make the value of slip equals to 1, right? So with the further increase in the slip, this will occur. There is a chances for the slip to become 1 if the load is, if there is an increase in the load. If there is an increase in the load beyond the maximum torque, there are chances for slip to become the equals to 1, right? So for example, if slip is made high, if Sx2 square is very large, if Sx2 whole square is very large compared to R2 square, then R2 square can be neglected in this equation. In this equation now, R2 square can be neglected because Sx2 square value is very high compared to R2 square, right? So this equation, torque T equals to K SC2 square R2 by R2 square plus Sx2 whole square. We can neglect now R2 square. So obviously what will happen? Torque T equals to K SC2 square R2 by Sx2 whole square. So one term will get cancelled out, right? We will get torque equals to K E2 square R2 by Sx2 square. So in this equation, if you observe, all the terms are constant except slip. So here we used to get torque is inversely proportional to slip. This is previously what we got. Previously, and during low slip, torque became directly proportional to slip. But now if the value of slip is made, high equals to 1, now it becomes torque inversely proportional to the slip. So here from the region can be extended from S equals to Sm to S equal to 1 is called the unstable region. That region is called unstable region. So in this region, with the increase in load, slip again increases, but torque torque gets reduced. Very, very important. So this is the unstable region. In this region, torque is inversely proportional to slip. In this region, torque is directly proportional to the slip. So this is what all about the slip torque characteristics of the three-phase induction motor. In this entire derivation, already from your previous basics, we will start with the torque equation. Torque equals to K SC2 square R2 by R2 square plus Sx2 whole square. The first point is, if slip S becomes equals to 0, that is possible when if the rotor also rotates at synchronous speed. If slip becomes 0, in this equation torque becomes 0. That is one case. Another case is if slip becomes equals to R2 by X2. If slip becomes equals to R2 by X2, that is another case. At that point, the torque will be maximum, called pull-out torque. Now another case where the slip value will be greater than Sm and it will be less than 1. So if the increase in the load, there are the chances for the slip to become 1, right? Then the torque decreases, right? So that is the unstable region for three-phase induction motor. These are the key points, right? Thank you.